Hey hackers, Nerdwell here, and I spy with my hacking eye something small and square with 8 little legs. Can you guess what I'm thinking of? Well, if you're here to watch this talk, you probably already know that today we're going to be looking at Spy Flash for bug bounty hunters. And we'll start with a review of what exactly is Spy Flash, how does it apply to us as bug bounty hunters, what can it provide us in our hardware hacking efforts? And then we'll do a few demos to show how we can read the contents of Spy Flash using off-the-shelf, inexpensive components that you may already have lying around. So what is Spy Flash? Well, it is a solid-state memory that's usually in a very small form factor, hardwired, soldered onto embedded systems and hardware devices, and it is usually integral to the operation of those devices. And SPI is actually an acronym for Serial Peripheral Interface, which is a synchronous serial communication protocol that's used in embedded systems and usually only works over very short distances and requires a minimum of 4 wires. Sometimes we can see instances of the protocol that use more than that, but at a bare minimum we will need 4 wires, and we'll take a look at what each of those is here in a moment. As you can see in these images, the Spy Flash chips are generally very small, and in most of the implementations that we will be encountering in our hardware hacking activities, you'll find them in 8-pin form factors. Speaking of our hardware hacking activities, let's talk about some of the common uses for Spy Flash that we might encounter. So Spy Flash usually has a relatively small capacity of storage. So sometimes we will see it used as the sole memory for small footprint devices with minimal storage requirements. What comes to mind are things like light bulbs and other IoT devices. And in those instances, we will see that the device may actually just run the code for its firmware right off the Spy Flash. But more commonly, the device will load the contents of the Spy Flash into RAM and then execute the code from RAM. Another common instance that we will see is that Spy Flash is used as the bootloader ROM for more advanced hardware devices like routers and Wi-Fi access points. And that's actually what we're going to take a look at today. And in these instances, what we'll see is that the router or AP will have a larger capacity memory device like NAND flash, which can go up to somewhere around 8 gigabytes or more. It takes a 48-pin socket and has quite a bit more complexity to dealing with that memory. And so the system needs some basic functionality to load up first that it can use to interact with the NAND flash, load its operating system, and then run from there. And so what we'll see is in a lot of cases that basic functionality that is used to read from the NAND flash and move to the next step of the bootstrap process is provided by the contents of the Spy Flash. Even in your most advanced systems and servers today, you will see Spy Flash very commonly used for like the PC BIOS. So even in an Intel machine that you go buy at the store today or build yourself, if you look on the motherboard, you will almost certainly find an 8-pin Spy Flash chip that has your BIOS loaded on it. And we will also see it in common modern peripheral devices, so RAID controllers and anything else, graphics cards, anything that you can put into a PCI X slot or USB device will commonly have some sort of Spy Flash that holds the firmware for its integrated controllers that are local to that device. And so, as you can see, we will find Spy Flash in all sorts of different places. And what exactly we can do with the contents of the Spy Flash once we extract it will vary from one device to another. And in some cases, We may even find it useful to be able to modify the contents of the SPI flash. For example, let's say we have a device that has a bootloader that does some security mechanisms that we want to bypass. Well, if we can extract the SPI flash contents, make some changes and jump over those code paths and then write it back to the SPI flash on the device, we can circumvent those security controls. And that's a more advanced example. Today we'll be looking at just pulling the bootloader code off of a SPI flash chip from a Wi-Fi access point that follows the typical design of using NAND flash for a Linux OS and SPI flash as its bootloader that it first loads in order to interact with the NAND flash. So if you are new to hardware hacking, coming to it from web app hacking or mobile device hacking or even binary hacking, you'll find that there are definitely some different tools that you're going to need to get started. And we can generally break these down into physical disassembly tools and other tools that we need to actually interact with the electronic components. And so if you've ever tried to take apart any electronic device, you could probably relate to how difficult it can be to get that plastic pried apart without breaking something. And while it's somewhat inevitable in the process of hardware hacking, we will likely break some stuff. We certainly want to keep that to a minimum, obviously. And so a toolkit like I have depicted here, which is iFixit brand, and you can actually follow that link that's on the display there and buy that. It may seem somewhat costly, but it will save you a lot of money in the long run. And some of my favorite tools from this kit are the little opening picks, the little blue triangles, and then several of those little flat opening tools are very helpful for breaking apart the seals on some of those plastic components that you'll find enclosing many of your electronic devices that you're going to want to hack. Lastly, you're certainly going to need some tweezers or pliers because everything in hardware is getting smaller and smaller and smaller. And so you almost can't have enough tiny little bitty tools when you get down to it. And I highly recommend to invest in a heat gun, which is different than a soldering iron. A heat gun just blows hot air, and it's usually tunable based on the temperature of the air that you want to have it produce so that you don't fry components. But it's helpful for heating up multiple pins at a time so that you can lift a chip off of a board. Next, you're going to need some tools to interact with the electronic components themselves. And there are so many different types of gadgets that you can get for interacting with electronics and doing hardware hacking. Many of these tools will simplify the process or combine multiple capabilities into one tool. Some of them can actually get quite expensive. So what we're going to focus on today are the essential tools that we're going to need to read from SPI flash. And I have intentionally structured this to use low-cost parts. If you've done any sort of Arduino, IoT, embedded system, electronic tinkering, then you may have a lot of this lying around. If you don't, you can order most of this stuff off of Amazon, or my favorite site for ordering this stuff is adafruit.com. And they're geared towards hardware hackers and tinkerers, and so a lot of their stuff is very user-friendly from our perspective. So what we'll need today to get started is an Arduino with a USB cable. We will need an 8-pin breakout board, which is this little thing at the bottom left-hand corner that you can see there, the blue board with the tweezers. And that's someone placing a SPI flash chip on one of these breakout boards. And we'll use that to make it more accessible and not have to worry about burning the pins on our chip. And that's pretty important, especially if you have like only one of the device that you're wanting to hack. You certainly don't want to damage the chip if you can help it. And so it's easy if you are trying to either solder or clip directly onto the SPI flash pins to break them off, and that's tragic. And so these 8-pin breakout boards are very helpful. You just solder your chip to that board, and then you have much more accessible pins that you can connect to, which we will try to use jumper wires anytime we can to make our solution more portable and flexible. And we'll need a breadboard. You will need a solder gun to solder only to remove the SPI flash chip and then solder it to your 8-pin breakout board. And then you'll need a Mac, Linux, or Windows PC to run the Arduino software and connect to the Arduino and ultimately read and display the contents of the SPI flash. At a high level, the process for reading the SPI flash contents that we're going to go through today involves some basic recon, then removing the SPI flash chip from the device, reading the SPI flash contents, and then making sense of what we have read from the device. These are super high level steps. Some of those have some sub steps, but we'll go into each of those here in a minute. But at a high level, this is the process that we're going to follow, and we'll demonstrate each of these steps as we go through. The first step is some basic reconnaissance. And you can do some things like look up the FCC ID of your device at a website called fcc.io. And on that website, you can find FCC filings, which a lot of times will include pictures of the outside and inside of the device. And a lot of times I'll start with that, but sometimes I will just start by opening up my device and poking around, taking a look. If we're looking for SPI flash in particular, as I mentioned before, it will usually be a 8-pin form factor. And so I will usually just start by using my solder gun or heat gun to remove these RF shields. And then under there are some chips. And I'll basically just grab the model number, part number, off of all the 8-pin chips and then Google them and determine what they are. And it's usually pretty easy to find. This is the device that we're going to be testing today. I'm not going to mention the manufacturer. Not that I have found any problems with it, but just out of respect for them. And so I did exactly that. I looked up all the 8-pin chip part numbers that I found on this and found a WinBond SPI flash chip, and this is the part number, W25Q256JV. And this is off the WinBond website, and I will actually pull up the data sheet for this. And as you can see, 3 volt, 256 megabit flash memory. You'll notice it says here it does dual and quad SPI. Those are more advanced. We're not going to deal with those today. Usually what you'll find is chips will support this in any modern system, but most of the time these are optional. They also will support just standard SPI. One key bit of information to grab from this data sheet is that the chip operates on 3.3 volts. So especially when you're dealing with like Arduinos and stuff, usually you'll find things will work either 3.3 volts or 5 volts. And so some of these SPI flash chips will actually be 5 volt chips, and some of these will operate at 3.3 volts. And it's pretty important to identify which is which for your particular chip, because if you try to supply a 5 volt supply to a 3.3 volt chip, obviously you run a pretty good chance of frying it. And then some other stuff that we'll get from this, let me go back up here just to table contents, is the pin descriptions and the pin out. So let me scroll up. As you can see here, this applies to a few different form factors. This is ours right here, 8 pins. And if you haven't done much with hardware, we'll cover a few things. This little circle at the top denotes pin 1. And so this is pretty standard for an 8-pin package. Top left, 1, 2, 3, 4, and then 5, 6, 7, 8. And down below here we can see what each of those pins does. And so I had mentioned in the beginning that most of the time SPI flash chips will operate with 4 pins, 4 wires. And what those 4 are is the chip select, which basically you can have actually multiple SPI flash chips attached in a chain to one quote-unquote SPI master. And so what the chip select pin does is let the SPI master tell each SPI slave, which in this case would be the SPI flash chip, hey, I want to talk to you now. And then when it's done talking to that device, it can remove the voltage from that chip select pin, and then it'll activate it on another chip. For our intents and purposes, usually we will not see multiple chips in a series or chained together on a SPI master, but we will still need to deal with this chip select pin. The other wires are data in, data out. So for our use case, we're only going to be doing normal SPI, which is 2 data, 1 data in, 1 data out. If you start doing dual and quad SPI, you can use additional data channels, but we will not need that for our purposes. And then the other of the 4 wires that I mentioned is actually the clock. And so SPI is a synchronous serial protocol. And by synchronous, we mean both ends need to share a common clock because they use the rise and fall of a wave pattern on that clock line to determine when to start and finish reading bits off of that string. And so that's what the clock line provides. Now, so that was 4 pins. We will actually hook up the other 4 pins. It's an 8-pin package. We will hook those up and we'll take a look at what those do here in a minute. But the 4 wires that are essential to the SPI protocol are the 4 we mentioned: chip select, data in, data out, and clock. So the write protect is used basically as it says. It's used to prevent you from overwriting the contents. Hold or reset, which in a lot of cases will occupy the same pin, are used to basically tell the chip to pause or not pause, as the case may be. And then we will see, go back up here. So that is 6 of the 8, and then of course the other 2, VCC, that's voltage in. So in this case, that's 3.3 volts in and ground. And there's lots of other useful information in these data sheets. I will go here to one in particular because we're going to use it, and that is the read data instruction. So as you can see here, it gets kind of complicated if you really dive into the details, but we can tell the SPI flash to do a whole lot of different things. Today all we're going to do is say, hey, we want to read some data. And so what that means is we are going to send it an instruction, and that instruction is going to be indicated by the number 3. And you can read some details here about how that works if you want. And as you dive into this, some of these details are interesting. Certainly as you get into hardware hacking, It's one of those things that can be a rabbit hole, but it can be a lot of fun. And so I would definitely encourage you to pick up on as much of this stuff as you can, and the stuff that you don't quite pick up on, just just kind of keep it in the back of your mind, and eventually stuff will start to click, and that is valuable background knowledge that you can use for other hacking targets. Now that we have a basic understanding of the SPI flash technical specifications and pinout, we're ready to remove it from the hardware device and put it on our breakout board so we can hook it up to our Arduino. The process of removing it from the hardware device is pretty straightforward. You can either use a soldering iron or a heat gun. If you use a soldering iron, basically just apply heat to each pin individually, and use a pair of tweezers to gently lift the pin up as you are heating the solder. If you use a heat gun, which is probably the preferred way, you will basically do one side at a time. So all 4 pins, you want to use a nozzle size on the heat gun that hits those 4 pins and not much else. And then you just hold the IC on either side with a pair of tweezers, apply heat to the 4 pins on one side and gently tilt the IC up, then remove the heat and do the same thing on the other side, and it will be free. This is a close-up of a device that I'm testing on. And basically, as you can see here, I have removed the SPI flash chip from this socket right here. I have wired jumper wires onto each of the pins so that I can attach my SPI flash chip to this device without having to resolder it back into the device. And the reason I do that is, in some cases, when I run into trouble, like reading from the flash, or I'm not getting what I expect, maybe I can read from the SPI flash, but the data that I see is not what I would expect to see. Then the question becomes, is it corrupt, or have I fried it? Have I done something in the process of reading it to damage it? And so being able to hook it into the original device quickly and easily gives me a way to test, basically a smoke test of, does this device work at all or not? Now let's take a look at how we ensure that we attach the SPI flash to our breakout board in the correct orientation so that we get the pin mappings correct. And when we're finished with this process, our end product should be a mapping of the colored wire to the pin function. So on the left-hand side, this is the data sheet that we took a look at earlier, and we can see from the pinout that, for example, pin 1 is chip select. And so we want to ensure that we identify pin 1 correctly on our SPI flash chip, and that we map that to the correct color and have that mapping for the next step. So the first phase of this process is to identify pin 1, which in this case is pretty straightforward. You're looking for the circle on the physical chip. And you will note that on the 8-pin breakout board, pin 1 is clearly denoted. And so as long as the circle on the physical SPI flash chip is aligned with the pin 1 marking on the breakout board, you should be good there. The next step is to correlate that to which of the pins on the breakout board the jumpers are connected to. And that's also pretty straightforward, as you'll notice in the upper picture on the right, in the empty breakout board, at the top left of that empty breakout board is a little circle emblem, and that denotes pin 1. So what I normally do is take a blank piece of printer paper, draw my device, a little square with 8 legs, and I just map them 1 to 1 to 1. Okay, 2 to 2 to 2, 3 to 3 to 3, 4 to 4 to 4. Simple as that. And this is something that you want to take your time with. It may be kind of tedious, but if there's any step in this process that you want to be a little bit tedious, it's this step. You want to get this right and everything else will pretty much fall into place. So at this point, I have a mapping. White is chip select. Blue is data in. Brown is write protect. Black is ground. Now I'm going to move up the other way. And this actually goes pin 8, 7, 6, 5. So red is VCC, gray is hold and reset, yellow is my clock, and green is my other data cable. So once we have that mapping, we're ready to move to the next step. That is all there is to removing the SPI flash chip from the device and preparing it to be read using my Arduino device. So just to kind of recap, basically we have physically disassembled our device. We have desoldered the chip. We've put the chip on a 8-pin breakout board, and then we have connected jumper wires to the pinouts on our breakout board. And then we have used the datasheet wiring pinout guide to determine which color of our jumper cables relates to which pin function on our SPI flash chip. And with that, we are now ready to read the contents of the flash. And so, as you see depicted in this picture, we don't need much. All I have is an Arduino, a breadboard, and my SPI flash chip, which is attached to that breakout board simply to make it easier to access the pins. Now, obviously it's a little difficult to tell from this picture what's plugged into what. So this diagram, and I can't take credit, I have to give credit here to someone else. This diagram is extremely helpful. If there's any reference that you take from this presentation, I would take this URL and bookmark it. As you can see on the left, we have the Arduino. On the right, we have the breadboard with our SPI flash chip. So the red wires are VCC, 3.3 volts positive coming from our Arduino. The blue wire is, or the blue lines are ground. And so as you can see, we have several pins are attached to VCC positive. So starting at the top left, the green one, that's 1, 2, 3, 4. So pin 3 is connected directly to VCC, 3.3 volts. And if you recall from our pinout, that is the write protect pin. At the top right, that was the VCC pin. That's voltage in. Obviously, that needs to be connected to VCC. And the next one down is the hold reset pin, which, if you recall, is what tells the chip to pause or not. And so if it has voltage applied, it does not pause. If voltage is not applied to that pin, then the SPI flash chip will actually not perform any instructions we tell it to do, which of course is not what we're going for here. So we go ahead and wire all three of those to VCC. And then the blue wire is ground. So that leaves us with 1, 2, 3, 4, 5, no, just 1, 2, 3, 4 pins left, which are our 4 wires that we mentioned at the very beginning. Chip select, data in, data out, and clock. So now we're going to take a look at the code that we're going to put into our Arduino to read off of this SPI flash chip. Before I move on though, I am going to point out the pin numbers on the Arduino that those wires are connected to actually do matter. So we need to know that chip select is plugged into pin X. Data in is plugged into pin Y. Clock is plugged into pin Z. And we'll take a look at what those pin numbers are here in a second. I actually don't remember. But what you'll see is the code corresponds to this diagram. So if you wire it up as is depicted in this diagram, the code I'm about to demonstrate will work for your SPI flash chip, assuming it follows the same pin out as this particular chip does. Now that we have our SPI flash chip wired up to our Arduino, we will take a look at the code that we're going to program into our Arduino to read that SPI flash contents. And you can do this on a Mac, Linux, or PC. Basically, you just go to arduino.cc, download the little Arduino development environment, and you can paste this code in there. We will start by including the SPI.h library. This provides some basic functionality for SPI communication, and then we'll define our pin names. What this allows us to do is refer to the pins by name for ease of reference in the code, but also if we want to change the pins that the SPI flash is attached to the Arduino on, then we can change it in one place and it will update throughout the code based on those macros. Lastly, we define the read instruction as the number 3, and we'll reference that in the code. And we define some variables here that we're going to use later on. A quick overview of Arduino code structure. Basically, there's two primary functions, the setup function and the loop function. The setup function runs once when the device powers on, and then the loop function is where you put most of your working code that's going to run on every cycle of the microprocessor. So in our case, we're going to do a little bit of initial setup in the setup function. Basically, we're just going to define what the pins do, whether they're input or output. We're going to do some initial SPI communication initialization, and then move on into the loop where most of our functions are going to happen. In the loop, basically we are just reading the contents and dumping them to a serial port, the COM port on the Arduino. And in the Arduino environment, we can open the serial monitor, which basically reads the data that's being dumped by the Arduino to the COM port over USB. And in our case, we are reading each byte from the SPI flash, writing it out in 64-byte rows, and then printing that to the COM port. So by opening the serial monitor, we have our output. We do want to turn off timestamps and make sure that we set the speed of our COM port to 115/200, which is what we set it to in the code. Then with that going, basically we click at the top right. In the right-hand portion of this window, we click at the top left, the yellow circle there. Basically that uploads our code to our Arduino, and then it immediately begins to run. So when I click this button, it will upload, it will run on my Arduino, and then it will start dumping the contents of the SPI flash to the serial monitor window on the right. And if you look closely, you may notice a pattern, a common pattern to the layout of this data. Obviously, it's moving too fast to read the specifics, but if you've done any binary hacking, you may recognize an overall structure to that blob of data. If not, no problem. We're going to take a look here in just a second. So I'm going to go ahead and copy this and put it in a hex editor. Scroll to the top, and as you will see from the header there, this is a standard Linux ELF format executable file, which is pretty common for bootloaders. If I scroll down a bit, we'll start to see some dependency library references. And so basically, we can get a quick look at this file and tell what it is in this instance. Sometimes it's not quite so easy. If it is a file system, for example, it will generally be compressed, and so we won't be able to read a whole lot of data straight from the raw file. But in this case, we luck out. So, to wrap things up, how do we make sense of the contents that we have dumped from our SPI flash chip? Well, in today's example, we could tell from the header that it was a standard Linux ELF format executable. And in a lot of cases, for bootloaders, that is exactly what you'll find. But for other types of devices or other instances of SPI flash use cases, you may find other file types or entire file systems on the flash chip. So how do you go about determining what you've pulled off this device if it's not quite so obvious? Well, the first tool that I like to use is the Linux file command. If you see that there is some data there, but you don't recognize like a header or a magic number, then you can use the file command to quickly determine if it is some known file type based on the initial file header. Or you can use XXD to simply dump the contents and search for known strings, known magic numbers. That's a rather cumbersome task, but sometimes it's helpful. Another Linux command that I don't have listed here that can give you some insight is simply strings. If you run strings on the file, you'll get a list of all the identified ASCII strings, and that may point you in the right direction. But if you get to a point where you don't really know what you're looking at, a super valuable tool is binwalk. And you can just Google this to download it. But basically, it walks the binary data and identifies all possible files within that binary blob based on well-known magic numbers for file types. And where I see this being especially helpful is when the SPI flash contents include an entire file system. What you'll see from binwalk a lot of times is it will identify what that file system is, and then that can lead you down the appropriate road to mount that file system on your machine and then read the contents of it. Lastly, if you just want to edit the file or search the file with a more user-friendly interface than XXD, there are some hex editors that are super useful. The one I used today was called HexFiend, and it's available for Mac and Linux. If you're in a Windows environment, Ultra Edit is a good tool, but I think it's pay for. There's a freeware version, but it's somewhat limited. And if you get the Visual Studio free version, it actually has a pretty good hex editor built in as well. So of all those tools though, binwalk is absolutely the most useful if you don't quite know what you're looking at. Well, thank you for joining me today. I hope that was fun and informative. Maybe even whet your palate for some hardware hacking. Feel free to reach out if you have any questions. You can follow me on Twitter, and happy hacking.